Let's go now to review the third section for IPSEC. In this session, we will see IPSEC headers, security associations, security parameter index, security association lifetime, and perfect forward secrecy. Now, traditional IP headers do not contain the necessary fields in order to let entities exchange IPSEC information. So we need new header fields and new headers for IPSEC in order, for instance, to exchange negotiation parameters, SPIs, numbers that identify IPSEC conversations, integrity check values used for integrity, or sequence numbers used for anti-replay mechanisms, and many others. So we are going to use new headers for phase 1 and for phase 2 in order to be able to exchange this information. So let's go for phase 1 headers first. For phase 1 that is used for control packets, we're going to use the ISAKMP header. The ISAKMP header is defined in the ISAKMP RFC, and it is using UDP 500 as transport, and following this header we are going to see the ISAKMP header. This header is not fixed in size. It is actually able to grow as needed using what we know as payload. So we have this payload here, this payload here, this payload here. These payloads have a next payload field that points to the next payload. So in this way, the ISAKMP header can actually grow as needed. Most of the vendors refer to this header as the ISAKMP header. However, some vendors such as Huawei particularly call this header the IKE header. And that may be because the IKE version 2 RFC defines this header again using payload. So it is mostly the same as the ISAKMP RFC definition. So bear that in mind. We can see how this works in a real live lab. For instance, let's see how it looks for IKE version 1. In this case, we're using main mode that has 6 steps in order to negotiate phase 1 parameters, and quick mode that consists of 3 steps in order to negotiate phase 2 parameters. So we can see that it is using UDP 4500 followed by the ISAKMP header. Notice that Wireshark recognizes this header as the ISAKMP header, and notice that we can add payloads depending on what we need to do with ISAKMP, depending on the step, depending on what control packet we are exchanging. So the ISAKMP header can grow, and notice that after step 4 we cannot see the contents any longer because we are now encrypting data. So this data is protected from this step on, so we cannot see what happens on quick mode because the data is encrypted. Now compare that with IKE version 2. With IKE version 2 we have different packets still using ISAKMP, but we are using IKE SA init, IKE auth, and create child. Now let's talk about phase 2 headers. We can use AH, ESP, or a combination of both. Let's talk about AH. It is defined as IP protocol 51. It is known as the authentication header. You can use it in 2 modes, transport mode and tunnel mode. Tunnel mode is the default. In tunnel mode, we are going to take the original packet and add a new IP header plus the authentication header. The authentication header does not support encryption. However, it supports anti-replay mechanisms because it includes a sequence number. It supports integrity, and by integrity we're also supporting authentication of each packet because it includes an integrity check value within the header. It supports carrying SPI numbers. Remember that SPIs identify IPSEC conversations. Now, the downside of IPSEC is that it defines integrity by including the header. So this can bring issues because, for instance, if we use a NAT device, we are going to change the header. We are going to change the source IP address. So if this packet arrives and it was changed using NAT, when this destination device calculates the hashing, it will come up with a number that is different than the number that travels through the network using the integrity check value header field, and it is going to break because we actually changed the header with NAT. So the downsides of AH are that it does not support encryption. The integrity uses the header field for calculation, so it breaks with one-to-one NAT. And given we don't have here a layer 4 field, we cannot support NAT overload. Now let's compare that with ESP, or encapsulation security payload. It uses protocol number 50. We can use it in transport mode or tunnel mode. Tunnel mode is the default, so we are going to use our original packet, and we are going to add it a new IP header plus the ESP header plus the ESP trailer. Now the ESP supports encryption. And it is supported by adding a padding bytes to the trailer, because some encryption algorithms work only with fixed size and packet lengths. It supports anti-replay because it includes a sequence number in the header. It supports integrity and therefore authenticating of each packet because it includes an integrity check value in the trailer, and it is also able to carry SPI numbers. Remember that SPI numbers identify IPSEC conversations. So the advantages of ESP is that it supports encryption, given the integrity check does not include the header. It supports one-to-one NAT, so that is good. But given we don't have a layer 4 header here defined by IPSEC, we cannot support NAT overload or path. So let's see how these headers look like. Let's ping router 2 and see how packets look like using authentication header. So in this IPSEC session, we're using the authentication header. So we can see here this IP header that is encapsulating the original packet, the authentication header with these fields, next header, length, reserved, SPI that identifies this particular IPSEC conversation, the sequence number used for anti-replay mechanism, and the integrity check value that is used for integrity. Notice that given the authentication header cannot support encryption, we can actually go and see the contents of this encapsulated packet. We can see the ISAKMP details, the original IP header, the GRE encapsulation information. Let's compare that with another IPSEC session here, where we have actually an encryption mechanism in place. In this case, we're using ESP. So we can see that the protocol is detected as ESP. We can see the new IP header followed by the ESP header that where we can only see the SPI number, and everything else is encrypted. Let's talk now about security associations. These security associations are used because we need to keep a track of IPSEC sessions between peers. So when two peers have successfully established an IPSEC session between them, each device is going to create a security association for this particular conversation. So this router is going to create its own particular security association for this conversation, and this router is going to create this particular security association for this conversation. These security associations are data structures that include an SPI that identifies this particular security association, the destination IP address of the peer, a lifetime, the key management methods such as the Diffie-Hellman group, the encryption keys that are being used. These encryption keys are going to change when the lifetime expire, and the transform. Remember that the transform is a combination of encryption algorithm and hashing algorithms. We can see this information using these commands: show crypto ISAKMP SA for iKey version 1 phase 1, and show crypto iKey version 2 SA for iKey version 2 phase 1. And for in order to see this information for phase 2, we can use this command, show crypto IPSEC SA. So let's see, for instance, this security association for phase 1 here, show crypto ISAKMP SA detail. We can see that it is active, the encryption algorithm, the hashing algorithm, the authentication mechanism, the Diffie-Hellman group, the peer IP address, and the lifetime that it usually starts for at 24 hours for IQ version 1 phase 1. So let's see how we can see the security association for phase 1 for IQ version 2. So we can see the remote IP address, that it is ready, the encryption algorithm, the hashing, the Diffie-Hellman group, the authentication method, and the lifetime. For phase 2, we can issue show crypto IPSEC security association. We will see that for each conversation, we will have an outbound security association and an inbound security association. We can see the details for in phase 2. For instance, in this case, we're using AH with MD5, and for instance, in this case, we are using a different set of protocols. We are using DES as encryption and MD5 as hashing with this lifetime. Notice that the lifetime is a clock that is running when, and we are going to talk about lifetime later on. Now for phase 1, we are going to only negotiate one security association that happens to be bidirectional. And for phase 2, we are going to negotiate two security associations that happens to be unidirectional. Now let's talk about the security parameter index. When two devices set up an IPSEC session successfully, each device is going to create a security association. So in this case, router 1 is going to create this security association once the IPSEC negotiation is successful, and it is going to identify it locally with this number. It is going to share this number with its peer. So the peer will know that this particular security association that was created for this IPSEC conversation has this number. Likewise, router 2 will create a security association once the IPSEC negotiation is successful in order to identify this particular conversation with router 1. It is going to create a number that uniquely identifies this security association locally, and it is going to actually share this number with its peer. So in this way, when router 1 wants to send a packet that belongs to this particular IPSEC conversation to router 2, it's going to add this particular number that router 2 shared previously. This is known as the SPI. In this case, this will be the outbound SPI. Now, router 2 is going to do the same when trying to send packets to router 1. When these packets belong to this particular IPSEC conversation, it is going to add this number, that happens to be the numbers that router 1 shared previously. So this will be the outbound SPI from the standpoint of router 2. We can see the SPI's numbers. So for instance, we can go to router 1 here and include the SPI's. And we can see, for instance, that the outbound SPI for router 1 is the SPI that ends with 5F0D. That happens to be the inbound SPI for router 2. And likewise, for router 2, the outbound SPI for this particular conversation ends with 9896. That happens to be the inbound SPI for router 1 for this particular conversation. So these numbers are, under this logic, interchanged. So each router will know what SPI number it will use to send packets to the peer and what SPI number it is expecting when receiving packets from the peer when these packets belong to this particular IPSEC conversation. Now let's talk about security association lifetime. Security associations have a lifetime. If we use shorter lifetimes, this makes IPSEC more secure. So shorter lifetimes make IPSEC more secure, but more CPU is used. The phase 1 lifetime is usually 1 day by default, and the phase 2 lifetime is usually 1 hour by default. So when the association lifetime expires, encryption keys are exchanged again, and they are exchanged using phase 1. So we can see the expiration time. For instance, for phase 1, we can use show crypto ISAKMP SA. This is the expiration time for IQ version 1. For IQ version 2, we can see this is the lifetime. For phase 2, we can see the lifetime here, lifetime. Now, we use Diffie-Hellman for both phase 1 and phase 2 by default. So, Diffie-Hellman ensures keys are created and shared securely over an untrusted network. Configuring a Diffie-Hellman group is mandatory for phase 1 and it is optional for phase 2. So the bottom line here is that Diffie-Hellman is crucial for the new key and generation refresh process. Phase 2, by default, phase 2 will derive its keys from the Diffie-Hellman that exists at phase 1. So by default, we usually have one Diffie-Hellman group that is created for phase 1, and this Diffie-Hellman group can create keys for phase 1 and phase 2 by default. So this process can be more secure by enabling perfect forward secrecy. So by using perfect forward secrecy, a compromise of a current session key does not compromise earlier or subsequent keys. What happens if a third party is actually doing it's recording an IPSEC session? It is going to be able to store this complete IPSEC session, for instance, on a hard drive, and the attacker may be able to eventually break a key. If it breaks a key, this attacker will be able to actually decrypt the IPSEC sessions that he stored previously. So over time, and a third party will be able to see earlier information or subsequent information for an IPSEC session if this attacker breaks the key. So that is the reason why security associations expire after some time. So after the lifetime of a security association expires, a new key must be exchanged. So by default, we only have one Diffie-Hellman creating keys for phase 1 and for phase 2. However, when enabling perfect forward secrecy, we are going to actually let the phase 2 to have its own Diffie-Hellman group. So in this case, this particular new Diffie-Hellman group is going to create keys for phase 2. So if the keys for the Diffie-Hellman that is running on phase 1 are compromised, we are going to be using a different key material coming from the Diffie-Hellman that is running for phase 2. So the bottom line here is that a separate Diffie-Hellman session can be enabled for phase 2 when enable perfect forward secrecy. We can see that, for instance, here when issuing show crypto IPSEC security association, we can see that we are not using perfect forward secrecy. No to perfect forward secrecy. However, therefore, we are not using a Diffie-Hellman group for phase 2. The Diffie-Hellman that we are using for phase 1 and phase 2 in this case is the same. In this case, Diffie-Hellman group 5. We can enable perfect forward secrecy, so we can have a separate Diffie-Hellman group creating key material for phase 2. So if a third party or an attacker compromises the phase 1 keys, he will still not be able to decrypt phase 2 data. So let's configure that. For instance, let's enable perfect forward secrecy using group 14. Let's say 14. We're going to do the same on the other side. Crypto IPSEC. We are going to enable perfect forward secrecy using group 14 on both sides. We are going to reset the tunnel. Shoot. And let's issue this command again. And we can see that perfect forward secrecy is now enabled. So we are now going to use Diffie-Hellman group 14 in order to create key material for phase 2. We are still using Diffie-Hellman group 5 to create key material for phase 1, but we now have a new Diffie-Hellman process creating key material for phase 2, and this happens only if we enable perfect forward secrecy. Now this is a summary of what we saw in this session. IPSEC headers, we saw that for phase 1 we use the ISAKMP header, known for some vendors as the iKey header, for instance Huawei. And for phase 2 we can use authentication header, we can use ESP, or we can use a combination of both. We saw what is a security association. Is a data structure that identifies a particular IPSEC session. It includes the SPI number, lifetime, and many other details such as encryption algorithms, encryption keys, and so on. We saw what is the security parameter index, which is actually this number, SPI. Two devices share the corresponding SPI to their peers. So we have an inbound SPI on one side, an outbound SPI on one side, and on the other side we usually have an inbound SPI and an outbound SPI. These SPI numbers are usually crossed in order for this to make sense. We talk about the lifetime. We saw that for IKEY version 1, for phase 1, the lifetime for security association is 1 day, and for phase 2, the lifetime for security association is 1 hour. And we talk about perfect forward secrecy, that we saw that by default we usually use one Diffie-Hellman process in order to create keys for phase 1 and phase 2, but when enable perfect forward secrecy, we are going to have a Diffie-Hellman process creating key material for phase 1 and another different Diffie-Hellman process creating key material for phase 2. That's it.